So, hello everyone. Today we are going to discuss about optimistic and ZK rollups. In the last lecture, I think Samrin discussed about what layer twos are and why they are useful. So today we'll be discussing the major two types, the optimistic and ZK rollups, and how do they work. So yeah, firstly, we will have to focus on some basic terminologies that are a must. Means whenever we are studying about the roll-up technologies, we need to know these terms. So first is the bandwidth. It's the cost of downloading and broadcasting the blockchain data. Then compute is the compute cost of running computations, and the storage is the cost of storing transaction data, whatever data we are storing on the blockchain. And these are the resources that a node needs, and based on these resources, a node calculates whatever cost will be required to run a node for any blockchain, be it Ethereum or any layer one blockchain. Then there are two parameters which are useful in measuring the performance of a blockchain. So first is the throughput. I think Samrin discussed that last in the last lecture. So it's the number of transaction that system can process per second. And second is the latency, the time it takes for a transaction to be processed. So these are the two important terms for measuring the performance. Currently, Ethereum processes a block for around 12.5 second, and it's 1 million gas per second. So you can calculate the throughput and latency there. Yes. So why do we need layer 2? Means we discussed in the last lecture that we have to scale the system, but why do we need it? So whenever we are creating a blockchain, our main purpose is to decentralize it. And the main things that we require in a decentralized system is that we should have little to low trust on the system for whatever transactions we are performing. That should not require any trust, and we should be okay with that. The cost of running the system should be very low, because if there are high costs, then we have to trust the system, because if there is a loss, then who will be answerable? So the cost of running the system should be low, and the system should be highly scalable. So scalable means that it should be able to operate for a vast amount of users, not just 10 or 15 transactions that are happening right now. So now scalable how? Like scalability can be achieved in many things, like uh, many apps are scalable. They are available to the users worldwide. There is Google, Microsoft, everyone is developing apps. They are scalable, but we want the scalability which is decentralized. We don't want to give the power in hands of one organization. So we want to achieve decentralized scalability, and that means achieving scalability without meaningfully increasing the system's trust. So the meaningfully increasing the system trust, I'll discuss what it actually means. And yeah, decentralized scaling is like we don't want to increase the trust on the system. We don't want to increase the cost of running the system. And yet, how we want to scale the system. Now, currently, as I discussed, the Ethereum's latency is 12.5 seconds and its throughput is 1 million gas per second. So, what does 1 million gas gives you? So, basically, right now, for 1 million gas, you can perform around 47 fund transfers from account A to B of ETH, and there can be around 16 ERC20 token transfers in a 1 million gas. So, per second you can perform at most 40 to 50 transactions, which is not we want to scale that. So now, how can we scale? So there are, like I discussed, we can use some direct solutions. Like we want to use an intermediary. So using an intermediary means like we'll take a third party, it will process all the transactions, and we will trust the third party that gives whatever transactions are happening. The third party is performing those transactions correctly, and the trust will be the major feature for using the intermediary. And second can be we can make the blocks bigger and more frequent. Like currently we are proposing a block in 12.5 seconds, and the gas limitation is there for 12.5 million gas. So the solution can be like increase the gas to around 50 million, and increase the block size so that we can include as many as transactions as possible. But are we able to solve the problem? Like, is it working? Because if we use an intermediary, then we are increasing the trust. And as I discussed before, we don't want to increase the trust of the system. Secondly, if we increase the block size, so if we are increasing the block size, we are taking in more transactions, more data. So the computation cost will be increasing significantly. And if the computation increases, then the cost of running the system is not remaining low. So that is the another problem that we can't achieve. So it is neither reducing the trust nor reducing the cost. So these solutions won't work. So now we'll think like how can we achieve this without increasing the trust and increasing the cost. So let's discuss from the first principles, like what happens in an Ethereum transaction. So in Ethereum, every there is a node, and every node is storing the state of the blockchain. A transaction happens, the state of the blockchain changes, every node calculates the state. They reach on a consensus that yes, the state change is accurate from all the nodes, and the blockchain moves to a next state. And during the execution, means the transaction is run through the EVM. We all know that all the transactions are run through the Ethereum virtual machine, and the transaction alters the state of the EVM. We reach to a state T plus one, which is agreed upon from all the nodes. So in this way, a transaction is processed in the Ethereum blockchain. So is it possible? Like the cost we are incurring is because we are interacting with the Ethereum state. So can we make a transaction without touching the state? Like just keeping the resources cost low without touching the state and yet performing transactions at a very high margin. So yes, the answer is yes, we can do that. So how are we going to do that? Yeah. So the first solution is optimistic rollups. So what are optimistic rollups? So optimistic rollups improve the throughput and latency. And how do they improve that? They move the computation and data storage off chain. So let's say there are two users, Alice and Bob. They are performing multiple transactions between each of them. So Alice sends 10 ETH to Bob, then Bob sends 5 ETH to Alice, and they performed around 100 transactions between them. Now, ultimately, there will be some changes in the account balances of Alice and Bob. What we are trying to propose is whatever 100 transactions that Alice and Bob used, means performed within both of them, will be storing the final state of the blockchain, and that final state will be submitted to the layer one, that is Ethereum in our case. So what we'll do, like as we said, we are moving the computation and data storage offchain. So whatever computation happened between those 100 transactions, when Alice sent some ETH to Bob, Bob received some ETH, he sent it back. Whatever computation happened, whatever data storage was there, we'll take it off chain. And this is not happening on the Ethereum blockchain, because when we perform the transaction on the Ethereum blockchain, the state change will be there and cost will be incurred. So we took all the transactions off chain, we performed all the transactions, and finally, whatever the account balance was, we submitted the final state back to the Ethereum blockchain. Now, the cost incurred for 100 transactions is reduced to a single transaction cost. Whatever state change happened between Alice and Bob's account, we have submitted that to Ethereum, and we covered up the cost of around 100 transactions. Now, how is this happening? Like, how are we using those 100 transactions and yet not losing anything? So this is done through sequences. Now sequences are responsible for storing and executing the user submitted transactions locally. So whatever transactions Alice and Bob performed, they were submitted locally through a sequencer. Sequencer ran all through all the transactions and changed the state of the Ethereum, which was initially to say state A. 100 transactions were performed. We raised a state B. We submitted that state to the L1 blockchain, and the L1 blockchain will verify whether the state is correct or not. We'll discuss that later. And finally, the 100 transactions are processed. So in the diagram, you can see, so the diagram explains like how can we enter a layer two or a optimistic rollup. So I am a user. I deposit 10 ETH to a bridge contract. Now, whenever you are entering a optimistic rollup or a ZK rollup, there are bridge contracts on the layer one blockchain. So if you are, say, depositing 10 ETH from the Ethereum blockchain to the Arbitrum or Optimism or Starknet, whatever L2 blockchain, so ultimately what you are doing is you are providing that fund to a bridge contract which is stored on the L1 blockchain. So this bridge contract will lock the 10 ETH. This transaction will be added to the sequencer, and the sequencer reads the transaction. It relays the transaction to another bridge contract, which is on the L2 blockchain, be it Arbitrum, Optimism, Starknet, any of them. The the equivalent amount of funds will be minted on the L2, and they will be transferred to the L2 address, where whatever address you have on the L2s. So, any doubt till now? Anyone? Okay, I think there is no doubt. Okay, let's move on. So yeah, we have entered the rollup. Now we'll be using the rollup. Now in using the rollup, what is means is like yeah, let's discuss this diagram. So there is a batch transaction on L1. The pre-state route something is there, the post-state route something is there. Alice made some transaction to Bob. Alice made some transaction to Charlie. Bob made some transactions. All those transactions happened. We created a state route. Now as I discussed earlier, the state route will change depending upon all the transactions that are happening. So initially, the state route was say 0x1345x7. After all the transactions, the post state route is 0xBC892F. Now, the variable is changed to the new state root. Like the new state root is BC892F. Now, the new state root will be submitted to the rollup contract. This rollup contract is on the L1 blockchain, and the new state root will be verified on the L1 blockchain. And in this way, all the transactions that happen between Alice, Bob, and Charlie, they will be verified that yes, they were correct. The new state root that we have achieved is as per the transactions that have happened. And in this way, all the transactions that were performed off chain on Arbitrum or Optimism, whatever they are being verified on the layer one. So, yeah, when we are submitting this batch, one thing to keep in mind is that these transactions are in a very compressed form. This is meant to reduce the storage cost that we are incurring on the L1 blockchain. So we are trying to reduce the storage as much as possible that we have to use on the Ethereum blockchain. So yeah, the note is there, like encoding of all the data is passed as call data. So yeah, how is call data working? Like whenever there is a contract on Ethereum, there is a method or a function in a smart contract, and the function takes some arguments. Now, these arguments are stored in the call data, and call data does not interact with the state of the blockchain, but we are able to store that call data in historical logs. So, in this way, we are reducing the cost. Like we are not interacting with the state, but still we are able to transfer that data to the Ethereum blockchain and store that in the logs. Yeah. This means that the published transaction data is not interpreted, executed, and no state access is made. It's just stored in the historical logs of the blockchain. Means if you have studied about how events happen and how we are logging the events on the blockchain, so we are making same use here. Like there will be some function called publish. It will take some bytes of call data, and its body is empty. Since its body is empty, it is not interacting with the state. Yet we are able to pass the transaction data as a call data, and the call data is being stored as historical logs. So in this way, we have stored the data in the form of logs, and yet we have not performed any transition to the state. So these are the cost-effective things that happen. And I have provided like this is the example of a log that like there's a transaction batch appended event, previous total element, sorry, a batch index, batch root, batch size, previous total elements, extra data. So these are all the arguments of the function. And in this way, we have provided all the data to the L1 blockchain in the form of the arguments. Like batch root, this is the batch root, then batch size, previous total elements, and whatever extra data. Okay. Now, in this way, we use the optimistic rollups. Now, exiting the rollups. So, how are we able to exit an optimistic rollup? So, initially, we were able to provide, means we submitted, say, 10 ETH to the bridging contract, and that fund was locked. Now, Alice wants to withdraw those funds, and she wants it back on the Ethereum mainnet. Now, how will she get back? So, firstly, she'll need a Merkle proof. That Merkle proof will be proving that yes, she has submitted some amount of ETH or whatever currency to the layer 2. Then the means for generating that proof, she'll be requiring the data for and that transaction data is meant to be provided by the sequencer. So it is the duty of the sequencer of every layer to blockchain to provide the data to the users so that they can generate a Merkle proof and give them the guarantee that yes, they have submitted some funds to the bridging contract. And if there is a malicious sequencer, we'll discuss how we are accommodating that thing. Now, yeah, here there are just assumptions on the sequencer that yes, sequencer will provide the data to the users. Now, how the trust situation is being solved? Like we want minimum trust, as low trust as possible. So the optimistic rollup solve this problem by requiring sequencer to post full transaction data on the main execution layer. And if they'll not post the data on the main execution layer, so there is something called means they have to put some amount there, which will be slashed. So in this way, we uh, means maintain the sequences that they have to submit the data to the main layer. Yeah. Okay. So now, how are we able to means how are we able to get confirm that yes, all the transactions that are happening are correct? Like the transactions between Alice and Bob that happen, say they both are acting maliciously and they want to provide a false state to the main L1 chain. So how are we mitigating that? So there is something called fraud proofs. We have a complete lecture. Next lecture is completely on fraud proofs. I'll discuss in just a gist like what happens here. So it is a cryptographic proof, and it demonstrates that yes, some fraud took place. There was some a transaction which was not up to the mark. It was altering the state in a way that we were not expecting. So there are some entities called verifiers. The verifiers, because they have available all the data, all the transaction data, they run through all the transaction data and generate a verified state themselves and match that state with the state which has been submitted by the sequencer. Now, if those state will match, the state is correct. But if the verifier finds a state which is not up to the mark to the sequencer state, the verifier can generate a issue that the state proposed by the sequencer is not correct. And in this way, we are providing a fraud proof. So if they spot a discrepancy, they can submit the proof. And in the fraud proof, there are two important terms that we need to remember: fidelity bond size and dispute period reduced. So fidelity bond size, what it means? Like in a proof of stake, what happens is a user provides some funds at the stake that and providing after providing that stake, he assures us that he'll be performing all the things honestly. So here, whenever a verifier is raising an issue, the verifier will provide some fidelity bond in terms of any tokens, whatever have been decided by the layer 2 rollup. So the verifier will raise some fidelity bond, and after that, he'll raise the issue. So if the issue is not up to the mark, means if the issue is false, then the whatever fidelity bond the verifier raised, that will be slashed. And if the issue is correct, in the same way, the sequencer will be slashed of some of the fidelity bond, and that will be distributed among the verifiers. So this is fidelity bond. The size can be determined depending upon various rollups. And second is the dispute period duration. So what is dispute period? Means whenever the layer 2 is submitting the transactions onto the layer 1, there is a period which is provided to all the verifiers. Within this period, they can run all the transactions which are within the L2 block and create their own state, and this state should match with the sequential state. So within the dispute period, they have to complete all the state changes, and means they have to produce their own state and match that state with the sequential state. So dispute period duration can also be controlled by rollups depending upon what they want. Like for Arbitrum, it's around 6.4 days. So there is a duration of 6.4 days, after which all the transactions that happened on Arbitrum are considered valid and they are submitted to the layer. So these are the two parameters that are important when dealing with fraud. Yeah. So here is a dilemma. Like we discussed that whatever transactions that happen on layer 2, we want all those transactions to be correct. So whatever state the sequencer produces, we want that to be correct. So this means step one, if the system incentive work as intended, means whatever we have planned, all the things are going as per the plan. So in this case, nobody is cheating. So if nobody is cheating in the system, then there is no point in running the verifier, because if someone is running a verifier, he raises an issue, but there is no problem in the system. So the verifier will lose his points, as we discussed, the fidelity one size. So there's no point in running the verifier. But if nobody is running a verifier, then there is an opportunity for a sequencer to propose a false state. Because there is no verifier, the sequencer has the ability to propose a false state, and no one will counter that state. But if the sequencer cheats, then the system will no longer function as intended. So okay, let's solve this. Like, how are we able to solve this? Yeah. So we have concluded that there is no point in running a verifier because we are getting no incentive out of it. Means if we are running a verifier and the system is running as intended, we'll be receiving no rewards. Then what's the point of running a verifier? So the solution here is like, if someone has some Bitcoin, or someone is holding some ETH, or someone is holding, say, any token which has some utility, we're not discussing about meme coins. So if someone is holding any token which has some utility, the token has some price, and any person, the user, whatever means, whoever is holding that token, they don't want to lose the value of that token. Like if some means if something happens in, say, Arbitrum or Optimism, the price of that token will fall drastically. The market will significantly decline. So the incentive here is any one of the person can will be running a verifier because they want to hold their token. Means the value of the token should remain there. Like say I am running a DeFi firm and it is solely based on Arbitrum. Now, my DeFi firm is having some tokens, and if something happens on Arbitrum, the loss will be mine. I have launched the DeFi firm on Arbitrum, and a sequencer proposed a wrong state. The the loss will be of the firm that I am running. So, out of uh, storing any the means out of uh, proposing that yeah, I have to hold the value of the tokens, I'll be running a verifier because I don't want my firm to go down, and thus in order to maintain that value, I'll be running as a verifier. So in most of the layer twos, what happens is like uh, any firm that have launched their product on any of the L2s, they'll run a verifier because they want that the token value should not collapse. So this is how we are solving the dilemma because the verifier directly is not getting any incentive, but when they have launched their own firm or their own product, then the incentive is there because they don't want to lose the value of their own product. I guess that is clear. Okay, so we'll take a break and then we'll discuss about the ZK rollups. So yeah, now I'll discuss what ZK rollups are. So they are similar to optimistic rollups in one way that as we were batching up all the transactions in the layer 2 and then submitting them back to layer 1. But the difference here is like there we were optimistically believing that all the transactions are correct. And then there was a dispute period where any verifier can come and raise a issue. But the difference here is like that there is a proof generated for all the transactions that happen, and the proof will be verified by a L1 contract. And in this way, we are not optimistically believing that yes, all the transactions are correct, but we are using a cryptographic tool to verify that yes, all the transactions are correct, and at the same time, we are saving the cost because we are not providing all the transaction data to the Ethereum blockchain. So this is another thing like we are no longer increasing the trust. We are minimizing the cost, and yet again we are able to solve the issue of scalability. So yeah, they are similar to optimistic rollups. They combine a large number of layer 2 transactions that were executed off-chain, submit them as one transaction on the Ethereum. Here we are using validity proofs instead of the salt proofs, and these validity proofs instantly prove if transactions are valid or not. And then one thing that is problematic is like whatever optimistic rollups are there, they are directly EVM compatible because all the transactions that are happening are basically same that are happening on the EVM. But for the ZK rollups, we have to develop a EVM which is compatible to the ZK circuits, and that is something to take care of. And many blockchains are working on it, but still it takes some resource and some tools to develop a EVM which is compatible to the zero knowledge circuits. Yeah, Starknet and ZK Sims are some of the famous ZK rollups. Starknet uses Cairo as their language. They are not ZK EVM compatible. And ZK Sync IP is there. And yeah, how ZK rollups work. So as we discussed earlier, there are multiple transactions. We bundle them up. We create a batch of transactions. Now all the transactions are batched up, and there will be a contract will be generating a validity proof. That proof from the layer 2 will be submitted to the layer 1, and the layer 1 there is a verifier contract. The verifier contract will take the proof, and there will be some public inputs. Using the proof and the inputs, it will verify that yes, all the transactions are correct. The final state that we have reached is the state that should be there. And once the all the transactions are verified, they are submitted on the L1 blockchain, and yeah, the process concludes. So interaction between L1 and L2. What happens? Like some say there is a batch one. There are multiple hundreds and thousands of transactions. They are batched together. The proof is generated and some public inputs are provided. The public inputs include pre-state root, post-state root. The proof is already there. These all inputs are provided to the layer one. The verifier contract will take the inputs, will take the proof, verify that yes, the final states are correct, and then the transactions will be included in the block in layer. Huh. So what are the dependencies on layer one? Like how is the ZK rollup dependent on the layer one blockchain? So first is the transaction finality. Like we discussed before, the transaction will be considered final only when the verifier contract on the layer one blockchain is giving us a thumbs up that yes, all the transactions are correct, the final state is correct. So the transaction finality is dependent upon the layer one. Then the data availability. So as we discussed earlier, like we were providing the data, all the transaction data as call data to a function. In the same way, all the call data is provided to the L1 blockchain in the form of call data. And say anyone wants to roll another ZK, means he wants to generate his own state of the ZK roller. So he'll take the data from the Ethereum blockchain, whatever was submitted as the call data, and spin up his own rollup and verify that yes, all the states are accurately managed. And censorship resistance is basically using the security of Ethereum blockchain, means all the state changes that are happening. And that's why we want the ZK rollups to be EVM compatible, because then it's very easy for all the transactions to be more censorship resistant. Yeah. Then how the validity proofs work. So as we discussed, there is a validity proof that has to be provided to the verifier contract on the L1 blockchain. So how will the validity proof work? So a ZK proof is generated. What are the things that the ZK proof includes? First, it includes the Merkle tree root of all the transactions in the batch. Say there are 100 transactions, will generate a Merkle tree, and the Merkle tree root will be included in the proof. The Merkle proofs for transactions to prove inclusion in the batch. Like if a transaction is included or not in the batch. So we'll be requiring Merkle proofs for that. So that Merkle proof is included. And Merkle proof for each sender receiver pair in transactions. And a set of intermediate state roots. Intermediate state roots are helpful in generating public inputs. And since we want to give as less information as possible, we are talking about zero knowledge, of course. So we create some intermediate state roots, and these are helpful in generating the public inputs, which are helpful in verifying the transactions. So now how this proof is generated. So there are many techniques like ZK stacks and ZK snarks. There will be a complete lecture on how these techniques work, how we generate the proofs. I'm just explaining that whatever is included in the proof, and stacks and snarks will be discussing later. Now what happens after the proof is generated? The L2 operator, the ZK rollup operator submits the validity proof to the verifier contract on L1. Public inputs are also submitted. The verifier contract takes the public inputs, takes the proofs, and verifies all the transactions. Yeah. So what is the benefit from these rollups? So I've included the screenshots. It includes all the optimistic and ZK rollups. So you can see that for sending ETH, the Ethereum mainnet takes $0.82 as fee, but Starknet takes zero point zero 0.01, Optimism takes zero point zero 0.01, Arbitrum takes zero point zero 0.01. So these are the significant cost reductions that we are getting. And from all the technology that we are using, we have come to a conclusion that no trust assumptions are being included. And one more thing, like whenever a rollup is started, actually it has three stages. So there is a L2 beat framework proposed by Vitalik, and it includes three stages: stage zero, stage one, stage two. In the stage zero, all the operators are manually run. In the stage one, the operators are all the contracts running. And in the stage two, like if there is a optimistic rollup, so in the stage two, whoever is the verifier, there can be n numbers of verifier. Anyone can come and verify the state of the optimistic roller. So let me give an example. Like if there is Arbitrum, so currently Arbitrum 1 and Arbitrum Nova, they are in stage 1. So in stage 1, whoever are the verifiers, they are a selected group of people that we have to keep trust on. What is the problem that no and means anyone cannot verify the transactions? The problem is like they have a dispute period of 7 days. So if Arbitrum allows any of the means any user to verify the disputes, so what will happen is a delay attack will take place. Like say I am a random person. I go to the dispute period. I raise a issue. I know the issue is not correct, but the dispute will be lengthened. Then I will raise the issue again, so the dispute period will be extended again. So from 6.4 days to 12.8 days to n number of days. So this is a problem that happens, and that's why currently we have to trust a certain number of verifiers that have been selected by the Arbitrum DAO. In the stage two, what will happen is they will be able to allow any of the user to come and verify the stage and verify the transactions. So in the stage two, it is called no wheels rollup, and no wheels rollup means that it is completely decentralized. So yeah, that was some extra information. So yeah, currently most of the rollups are in the stage one level, and they are transitioning to stage two. And yeah, these are the benefits. Like the gas fee reductions are significant, and the swap tokens also it takes $4.1 on Ethereum, but on the means ZK rollups, it is significantly low. Yeah, one more thing you can notice here is like in the Starknet, it's 0.01, but in ZK Sync Lite, it's 0.04. In Met is in 0.09, 0.16. This is because it depends upon the proof that all the blockchains are generating, like we discussed about Starks and Stark. So the slight difference in the cost is because of the proofs. It depends upon the computation of different methods. So that is why you are seeing a significant difference in the price. Though it is very small, but yet there is a difference. And yeah, this is the difference between optimistic and ZK rollups. I have explained all of them. So optimistic uses proof proofs, ZK uses validity proofs. Optimistic requires a 1 week delay because of the dispute period. And ZK, we can withdraw funds immediately because valid data compression, it publishes full transaction data and it does not publish full transaction data. It is just giving up some public inputs. And in ZK rollups, one more thing that happens is like they are saving the transaction data, saving the storage cost by reducing the public addresses to bits. Like for a 20 byte address, they are using a 6 byte index and they are indexing all the addresses. So for two address, the initial cost would be of 40 byte. But what they do is they index the address through a 6 byte slot. And in this way, for every two addresses, they are saving 28 bytes. So in this way, compression of ZK rollups takes place. And the roll-up cost means these are the difference cost. Like for ZK rollups, they face high overhead cost because of the computation, the verifying rules. Optimistic rollup, trust resumption, it doesn't require a trusted setup. It requires ZK rollups require a trusted setup, like the cryptography has to be trusted that yes, the cryptography is working. The liveness requirement like the verifier should be there for optimistic rollups, but in ZK rollups we don't need someone because the verification is taking place through the verifier contract. Security properties, yeah, these are some basic things. Uh, okay, then I guess these are the differences, and these should be enough for you to understand what actually optimistic and ZK rollups are. We have upcoming lectures to explain all the details in much more depth. But yeah, this was the intro to optimistic and Jupyter. Any doubts?